So we have the semiconductor detectors, and we are going to discuss only the semiconductor detectors. So nuclear detectors, as you all know, that is a device which can actually detect nuclear signals, and based on this we have got something which is called the semiconductor detectors. Okay. So before that, we'll just go into the basics. I think we already know is about semiconductors, have been learning it from class 12 onwards. So whenever we say that there is a, because you're also doing your project work and so on, so we definitely have something which is called the valence band, and we have got the conduction band, right? And along this, what is the unit along this? What is the value? What is the parameter? Energy, right? So basically it's an energy, right? Yeah. So you basically say it's energy, units is mostly EV, right? EV. So we have the energy, mostly units are EV. Okay? So if we have this, and then we can have a smaller gap, okay? And then we basically call it as the, this is your insulator, right? Insulator. So insulator, we are just going to say some basic things. And this is
Semiconductor.
Semiconductor, and then we have got the metals.
No.
Okay? There are certain metals which is considered as metals, but they also have some kind of gap in between. Okay, it's not always mandatory that for metals the energy levels will always overlap. Okay, this is an image which is given in most of the books, but sometimes I feel this is not the exact way to represent it. Okay? Some metal also has got some kind of energy gaps that we have. Okay. So when we basically talk about insulators, and we have got the energy here, which is the EV, okay, and usually if this value is greater than some EV, we basically call it as the insulator. So what is the typical value above which it is called the insulator, and what is the typical value where we can talk also this is okay a semiconductor? So if we again differentiate semiconductors, these are also having a wide band of semiconductors, right? Yeah. So there is wide and narrow, okay. So this wide bandgap semiconductors, you can say anything about 2 electron volt or 2.5 electron volt basically comes into the category of wide bandgap semiconductors. Because sometimes we do feel that even if you consider tin oxide or zinc, all of their band gap is greater than 3.5. Now if it is greater than 3.5, it's quite a lot, okay. So we will see in this that how much energy is needed to actually create electron hole pair. Now before we go to that, let's try to understand here what exactly do we mean by electron hole pair, right? So my question to you is, an insulator doesn't conduct, right? So in a technical way, what is the best explanation? Why does an insulator doesn't conduct?
Conductivity.
Okay, what about the charge carriers, in terms of charge carriers? Does insulator have charge carriers?
Lone pair of electrons.
Okay, lone pair of electrons won't be the exact answer, but in terms of charge carrier, we can say any insulator doesn't conduct because it doesn't have any charge carriers. Okay, and whenever we say something that there is no charge carrier, it means that there are no electrons in the conduction band. Okay, so what happens is, if you have an electron, okay, what is these systems like? You have if you have a basic wire, okay, you have a wiring system, and you have an electron, correct? You have an electron. Will it start flowing? No, no. We need current because we need flow of charges. Will it start flowing all of a sudden? What should I do?
Give
potential, right?
Yeah.
Give some potential, give some positive, negative potential. There should be some difference of potential. Okay, this idea is very important because we are going to study about scintillation counter. There also it's the same logic. So what happens here is basically when we say there is something which is conduction band, it's not that there is some real band which you can look into. Okay, it's like if we have free electrons, that is considered to be in the conduction band. If we don't have any free electrons, they are considered to be basically in the valence band. Okay, all the electrons. So whenever we basically have any kind of semiconductors, they are insulators at room temperature. We already know. But what do I have to do to make it conductor? I have to basically give some kind of energy so that the electrons here can jump to the conduction band. In other words, it means that the electrons can become free. If the electron becomes free, then only we have that. On the other hand, if we consider metals, there are already free electrons. So once we apply a potential, straight away the current starts flowing. In a semiconductor, just with the potential, you might not have the current flowing. Okay. So this is where there. Now if we have an electron here, what we have here? Holes. Holes, right? So we already have holes here. Okay, this is these things you have already known. So these are all bit of revision. The next point is what do we mean by reverse bias and forward bias,
Yeah.
right? And which case we get more current and in which case we get less current, okay?
Oh.
So forward bias we get more or less more current, and reverse bias we get less current, right? So basically what we have is a reverse bias and a forward bias. Now when we are actually making a semiconductor for detecting nuclear radiation, okay, we don't want too many charge carriers of the semiconductor to take part. Getting it? If we have too many charge carriers of the semiconductor to take part, it interferes with the signal that I am going to detect. That is why what I need is a reverse bias. Because if we have reverse bias, we have got minimum current because of the semiconductor. So then when we have the nuclear radiations, it's going to give me a better signal. A nuclear detector based on semiconductor is in fact having a very good resolution. Okay, so what do you mean by resolution in general? Okay, I'm just giving you the introduction to these terms that you should know. Reverse bias, forward bias is very simple, you already know. So how do you do the reverse bias connection?
Negative to the positive.
Yeah, negative to the positive, positive to the negative, right? And forward bias you have just the other way, right? Positive to positive, negative to negative. Okay, the next part is that when we are talking about these electron hole, okay, when we have the gas detectors, what is the pair formation? In gas detector, what do we have? That will be explained.
Voltage. Oh, no.
No, no. What are the pairs that are formed?
Iron.
Yes, ions and electrons, right? So in gas detectors, we have got electrons and ions. And what we have here in nuclear detectors, okay, are nothing but electron and hole. So this is one of the differences between nuclear detector and gas detectors. Okay? So once we know these things, we can actually start off with the idea of how does nuclear detector work. We do have a schematic, okay, and based on this, we can actually understand a lot of properties. So one last thing, like would be a depletion layer.
Yeah.
A depletion layer. So we have got something which we call as a depletion layer. So depletion layer is very critical for semiconductor nuclear detectors. What's the reason? The reason is the radiation that is incident, the alpha particle or the beta particle or the gamma rays are incident on the depletion layer. So broader the depletion layer, better is the detection. Okay? Now when we get broader depletion layer, when it is in reverse bias or forward bias?
Reverse bias.
Correct. Reverse bias, okay? We have a broader one, okay? So we are going to explain that, don't worry. But what is depletion region in general? It is the region of immobile charges. Okay? All of us remember about recombination, right? So what happens is charges from the p type will diffuse towards depletion layer. Charges from n type will diffuse towards the depletion layer, and both of them will basically form a pair. So it will be a region of immobile charges. So it's a region of immobile charges, right? So if you consider a semiconductor, okay, and we have got a p type and an n type, then how do we connect it in reverse bias? So this is negative and this is positive. So this is basically a reverse bias condition, right? So if we have this is p type, and we have some diffusion of charges. Okay, we have got some diffusion of charges, and these diffuse charges will move here. So we have the p type, and these are the diffuse charges, and we have the n type, and we have got the negative charges here, and this is going to form a region of immobile charges. Okay, so this is a region of immobile charge. Now what do I need to do so that I can have the charges mobile again? I can put some energy.
Yeah.
And that energy can be in the form of nuclear radiation. Once the nuclear radiation goes in, it basically have an electron and a hole pair. Okay? And that will basically give you a potential drop. And that is the entire logic of semiconductor detectors. It has got many advantages over the gas filled detectors. Okay. So before we proceed, we can just draw a bit of schematic. It's not a very difficult diagram. Okay. Just going to draw that figure, and then we were going to revisit whatever concept we've just discussed. Okay. So what we have is we have a semiconductor. So let's say this. So this is an N-type semiconductor. Let's say. And let's say some design is there. So this is P-type, okay, and then we have got to connect this across a road resistance RL. And since this is in reverse bias, so this side we are going to get a positive end. So this is our depletion region. So the depletion region is our hero for the nuclear detection here. Okay, it's important. So this is a very simple diagram that we have. Of course, we have got more electronics into it. Okay. So how do we get a P-type semiconductor and an N-type semiconductor? I think we already know these things. Okay. So can we get a P-type and an N-type semiconductor from the same host material? From the same host material, can we get a P-type and an N-type? Yes, by doping, right?
Yeah.
Right. We dope it by a trivalent, okay, and you can dope it by a pentavalent material. Okay? If you dope it by a pentavalent material, you basically have a N-type, and you've got dope it by trivalent, you get a P-type, right? And so on. So these things are very basic to semiconductors. So this is the basic idea of the detectors that we have in semiconductors. What happens is usually you have the radiation here, let's say for alpha particles, okay, incident in this depletion region, and we have got formation of electrons and holes. Okay. So as we know that the energy is more, we are going to form more and more electrons and holes there. Okay. So since we already know about the depletion there, if we just want to write down exactly how we are supposed to produce it in our exam, we can just draw this figure, okay, and explain some basic things here. Okay, I'm not going to write down these because these you can explain on your own words if the question comes. So we have got an N-type and a P-type semiconductor which is connected in reverse bias. So when you draw the circuit diagram, don't make the mistake, because P-type is connected to negative and N-type is connected to the positive across the load RL. Okay. Once we have that, we can explain what is depletion there. So what happens? The positive charges will diffuse towards this region, and the negative charges will diffuse towards this region. Because of this, this is going to create a region of immobile charges. In semiconductors, if you want to get a large current, it's important that the charge carriers usually crosses the barrier, right? So if you have the positive charges here, it should cross the barrier, the negative charges should cross the barrier, then only you are going to have the current here. But since this is connected to the positive one, so it is already going to flow in this direction. So you are not going to get it in the other direction, right? So what is going to happen because of that? Only minority charge carrier takes place in your conduction process, right? So if there is only minority charge carriers, you are going to get minimum current, right? So what happens here? We have reverse bias, minority charge carriers, right? So these are minority charge carriers. And minimum current. This is a happy situation for me because I want the system to work, I want the system to conduct, but I don't want it to have its own current. because I want to detect a signal. Okay. Next, what happens? I have the alpha radiation or gamma rays. Okay. Mostly it's alpha and gamma. Okay. Most of the times. So basically comes and hits here, and it basically forms an electron and hole pair. So now we have got electrons and holes there. This is going to flow across this, and this is basically going to change this signal. So we are going to have a potential change across RL. This change will result in a change in the signal, output signal. So this is difficult. It's a different electronics altogether. We do have an amplifier now, okay, a signal reader now, okay. So we have this. So these things are connected here, which reads the signal. So as soon as the radiation enters, we basically have a change in the signal, which is studied, which is because of the semiconductor detector. Now the question is, this is somewhere similar to the concept of gas detectors, but why it is beneficial, okay? So these are some of the points that is important, okay? So the minimum current is a very important factor, okay? So what are the factors that makes it efficient? Minimum current because of reverse bias, okay? Already written on top, but let's write down this again. Reverse bias. So this definitely reduces the noise, okay? Definitely reduces the noise because we have got a less current over there, okay? Okay. So what is the energy of alpha particle? Typical energy of alpha particle? Remember, we discussed missing energy concept in alpha particle theory. Okay. So there was some typical energy. We have drawn that energy versus potential graph, 4 to 9 MeV.
9 MeV.
You remember?
Yeah.
Okay. So we have got the typical energy is 4 to 9 MeV. Now, for electron hole pair, how much energy do you need? Okay. Now this is the basic catch here. So energy needed for electron hole pair. For this, you need just 3 eV of energy. You get that? Okay. So if you have an energetic particle like an alpha particle, okay, which is having an energy of 4 MeV, but the energy needed for a single electron hole pair is just 3 eV. So that means that alpha particle is going to generate a number of electron hole pairs. And if we have so many electron hole pairs, definitely the drop or the change in potential is going to be more. And there is no electrical signal as such from the system because it's in reverse bias. So the detection of signal becomes very, very easy. Right? Okay. But on the other hand, so this is for nuclear detectors. Nuclear detector. Okay. But on the other hand, if we consider this ionization chamber or proportional counter and so on, right, you are going to create an electron ion pair. Knocking out an electron from an atom takes much more energy. Okay, it needs more energy. Okay, so energy needed for electron. Okay, sorry, this is not E plus, E minus. Electron ion pair is approximately 35 electron volt. Gas chambers. Gas chamber detector. Ten times more. So that means by the same alpha particle, the number of electron ion pair which is formed in a gas chamber, which is the basis of detection of nuclear radiation, you are going to get 10 times more electron hole pair in case of semiconductors. That means this is much more sensitive. Right? We need sensitive instruments. Correct? So that's one of the major advantages there. Okay? That's one of the major advantages. So for nuclear detectors energy, which is 3 eV, is 10 times lesser than gas detectors. So if you consider an alpha particle, for an alpha particle, please write it down properly in exams also. Okay. For alpha particle, we have got 10 times more signal, or 10 times better signal. For nuclear detectors compared to gas detectors. Okay, so please remember, if I ask you that what is the difference between semiconductor detector and gas chamber detectors, you have to remember these points. Okay, already the points on the board. First is, in case of nuclear detectors, electron hole pair is formed. In case of gas chamber detectors, electron ion pair is formed. Okay, for nuclear detectors the energy is this much needed, obviously, because it's a semiconductor detector, and hence it creates 10 times better signal for nuclear detectors compared to gas detectors. Okay, so if you write down the comparison, it doesn't mean that one side you have to write down semiconductor, one side you have to write down the nuclear detectors, okay, or the gas chamber detectors. You can just write down a normal paragraph for that. Okay, just explain it, write down the paragraph, that's all. Okay, probably a 2 marks question or 3 marks question, not beyond that. Okay, if I ask you to difference. Okay, so is it clear, the duty of semiconductor detectors? Okay, now what are its advantages? We can already seen some advantages, but let me just list down some more here. If you consider the advantages, so it can detect very low energy particles, very low energy particles. Is it right? Yes. Even if the alpha particle or the beta particle has got a very low energy, the amount of signal that it is going to generate is 10 times more. Okay, so that means we can even detect the beta particles more easily. Okay, so that's why it can detect the very low energy particles. Okay, number 2, better energy resolution. Better energy resolution. Okay, so imagine we have got what do you mean by resolution? What do you mean by resolution? So if you take a camera and we talk about resolution, okay, it's an optical phenomena. So obviously every device has got some resolution involved if it is going to do some kind of measurement. Okay, so when we say resolution in general, let's say consider in place terms of a camera, how well it is able to distinguish between 2 points which lie very close to each other. That is something which is called resolution, right? So you might have a gamma particle of some energy, okay, or let's say you can have an alpha particle of 3 MeV, and you can have an alpha particle of 4 MeV. They are nearby. I can have an alpha particle of 3 MeV and I can have an alpha particle of 3.1 MeV. Now using these kind of detectors, can I know what is the energy of each of these alpha particles? If I can know that, that means it has got a very good energy resolution, right? So what happens is, if the energy of example, let's say alpha particle is more, then electron hole pairs are more, and the signal is signal is more, right? But if the energy of a particle is less, electron hole pairs will be less in number and the signal will also be low, right? So I can distinguish very easily. Okay, so we can differentiate between two energies of incoming particle close to each other. Incoming particle close to each other. Of incoming particle, put it in bracket. You can distinguish between the energies of close to each other. So if we can do that, that means it has got a better resolution. Okay. And finally, it is small and compact. Okay, it's even smaller and compact. Wow. Yeah. So we have a small and compact system. Okay, so we have the scintillation detectors. Now, what do you mean by scintillation here? What do you mean by scintillation? You have an external signal falling on it, some energy. For example, let's say nuclear radiation, which is our sole purpose. It will excite, okay, the atoms, okay, and then when it de-excites, it's going to give out some photon, some radiation, okay. What is one of the material that you already know that produces this effect? One of the most common material where you have that scintillation effect. You have some radiation falling on it, it will basically give out light, okay, or signal. Zinc, it's something, a zinc compound, it's zinc sulfide, right?
Zinc sulfide,
So zinc
yeah.
sulfide is one of the most common, okay. So these scintillation materials are composed of different materials of these nature, okay. So we have got this, okay. So these are called scintillators. Scintillators. Okay. So let me not write down these things that electron jumps from conduction band to valence band. When it de-excites, it will give out the radiation. Okay. But in exam, if I ask you, you can explain these things because it depends on the marks. Okay. Depending on the mark, just do that justice. So you have got a cesium iodide scintillator, and this basically is used for proton and alpha particle, detecting proton and alpha. Okay. And then we have got sodium iodide. Okay. This is for gamma radiation. And then we have got the zinc sulfide. This is called the alpha particles. So all of us are very much familiar with the photoelectric effect. Okay, we have got a metallic surface. Okay, and when basically some radiations falls on it, electrons are ejected. Okay, so what we have here is a a scintillator, and we have got radiation coming in. Let's say an alpha particle, and let's say it's made up of cesium iodide or zinc sulfide, and then it's going to emit these scintillations, right? And this scintillation is basically going to hit the photocathode, right? And what photocathode is going to do? It's going to eject electrons. Okay, so we have got the electrons which gets ejected. Now, as the term suggests, we have got something which is called the photomultiplier tube. So whatever signal you have is basically generated from photons that is going to get multiplied. Because if I have got a very low signal, it is basically difficult to detect in a system which consists of a number of electronics there. There are other noises also there. So what is my aim? My aim is to increase the number of the signal. Okay. So if you have got two electrons and it is basically hitting a diode. These are electrons, right? So what is the potential of the diode here? Plus 100 volt.
Yeah.
So this is plus 100 volt. So basically these electrons are going to get attracted and hit the diode. Okay, and this diode is going to give rise to secondary electrons. Okay, going to give rise to secondary electron. So from one electron we can actually give rise to two electrons, and then this also will give rise to two electrons. Okay? Or more. Okay, 2 electrons or more. Okay, just as an example. Then what happens? This is 200 volt, this is 100 volt. So this is at a potential difference greater than this. Obviously, it's going to move towards this direction. If this was also at 100 volt, I would have never got this situation. So that's why it's important that the voltages keeps on increasing at constant rate. Okay, so we have in there. Next, what happens? This is going to again get you 2 more, and then this is also going to get you 2 more. Then this is also going to get you 2 more. And if you look into a typical book, you will have a better image than mine. Okay. Okay. So finally, when you are going to get the signals from this end and this end and so on. Finally, the signal that you are going to get, which is being accepted by this. Okay. So we have the anode which is accepting this, and this will be nothing but a number of signals. As a result, the signal gets multiplied. Is it clear? And then we can read that signal, and this is the output in the digital part. Okay? We have the amplifier and the electronics to check the output. So this is exactly how a scintillation detector works. Okay?